and I will chair the meeting. The other members of the committee are Professor Cheth, who's the major professor and advisor of Ms. Raute, um, Dr. Das, Amitava Das, who also works for was on the faculty here and on the AI Institute, um, Dr. Vignesh Narayanan at the AI Institute, and an assistant professor in computer science, and of course you from Adobe, as I understand. Very good. Thank
Yes.
you, Dr. Nankova. And if Professor Shath agrees, we can ask Ms. Raute to start the presentation. I would suggest that we keep questions during the presentations only to matters of detail and save longer questions, more in-depth questions for the end. Thank you, and let's start then.
Let's start with.
All right. Thank you, Dr. Valtoda, for the introduction. I'm Vipula, and my dissertation title is Hallucinations in Large Foundation Models, Characterization, Quantification, Detection, Avoidance, and Mitigation. And Dr. Sher, Dr. Valtoda, Dr. Das, Vignesh, and Ani are on my dissertation committee. These are the contents of my presentation. I'll be briefly discussing each of them. So we are already in the Gen AI era where every other almost research is happening in LLMs in particular and even beyond that. And why is this of specific interest? Because it's making a lot of impact and buzz. So this is something booming recently. And along with the merits, there are some challenges that come with these latest technologies. So these are some recent examples I have taken just to quickly illustrate. So Google lost some $1 million because of some fiasco done by the Bard chatbot, and this is one example. Then there is another hallucination example of Air Canada chatbot where the chatbot issued some refund where there wasn't any. So it just made something up. And these are some real world examples where chatbots or it just makes stuff up. And this is the problem of my dissertation so I'll just stop here. And so this is of particular interest to me because this is something has been quite a challenge for the LLMs. And if we go further, Hallucinate was also the word of the year in 2023. So my motivation for this line of research has been, I'll just quickly read this and then I'll go into what I am currently working on and what I have already worked on in the last year and early this year. So the recent progress in Gen AI, particularly LLMs, has laid the foundation for innovative applications. And then there are some challenges with LLMs. So to ensure safety and to have some kind of trust in these systems, we need some mechanisms in place. So my scope for the thesis is to come up with first of all, we need to quantify what we are doing. Then in particular, hallucinations is my topic of interest. Then I move on to detection, then avoidance, mitigation, and then even extend this work to multimodal. So the first part is already done and published. So I'll go to that slide soon. And then detection, avoidance, these are some techniques which we already have under review. Mitigation is something, it's ongoing work, and so is the multimodal part. So in multimodal, we'll be focusing both on images and video hallucinations. So I'll first start with characterization because this is something, an upcoming topic. We are one of the first ones to propose a benchmark and metric and so on. And this is something from last year. So this is the paper which got a lot of traction. It's called The Troubling Emergence of Hallucination in Large Language Models in Extensive Definition, Quantification, and Prescriptive Remediations, where if we see on the first page itself, we have a taxonomy where we proposed uh, the orientation, category, and degree. I'll go into the details shortly. And this paper also got some press coverage. So it was included in the Washington Post, an opinion piece where they took some parts from this paper. So specifically, there is one example for silver lining case. So this was included in that opinion. So this is the taxonomy where we bifurcate hallucination into two types. Uh, on a higher level overview, there is factual mirage and silver lining. Then we go into intrinsic and extrinsic. Then we have six specific categories. And then depending on how critical each category is, we define 3 degrees of hallucination. And this paper already has made quite an impact. It's already well cited. So I'll start with factual mirage. So just quickly to reiterate, I'll just give these examples and then think it will help understand. So factual mirage is when the prompt is correct, but it still generates hallucinations. And for silver lining, the prompt itself is incorrect and it should ideally say that this is incorrect, but on the other hand, it's generating some text. So intrinsic means it's generating some hallucination, but it's within the context of the prompt itself. So for instance, here, if I ask who was the first person on Mars, it says Neil Armstrong, but then he was the first person on the moon, not Mars. So the hallucination part here is moon, but it's not completely out of the context. So it's still giving some response which is still in the scope of the prompt itself. But on the other hand, extrinsic factual mirage, it generates some response which is slightly out of the scope of the prompt. Then for silver lining, the prompt itself is incorrect, but it's still generating some text, and which ideally it shouldn't, but it is. So similarly for intrinsic and extrinsic, so I'll just quickly go over this example because this is a little interesting. So the prompt is Kamala Harris and Elon Musk are getting married. So it should, the first, I mean, ideal response should be these two are two different people and they were never married or they are not in that uh, getting married zone, but still it's generating the response where it's generating a beautiful story and it's giving the venue and other details such as dates and so on. And the fact is, this incident never happened. Then moving forward, the second vertical in our taxonomy is where we identify the specific categories. And each category is based on what's being hallucinated. By that, I mean, so if in the generated response, the numbers are hallucinated, right? So we call it numeric nuisance. If the location is hallucinated, we call it geographic erratum. If there is some fictional character generated, we call it generated golem. If there is some issue with the acronym, we call it acronym ambiguity. if there is something which is being said by someone, but in reality there is nobody who said it, it's virtual voice. And then time wrap is when incidents from two different time era are being put in the same timeline, or something to do with the time temporal issue, yeah, basically. So there could be different variations here, but that's the basic idea behind time wrap. So if I quickly again go over each example, we'll see here. So Twitter is said to have laid off some X number of employees, and then it says the AI generated text says 8%, which is roughly 600 people. But then the fact is it laid off some 10%, which was some 200 people. So the issue here in the hallucinated part of the text is just numbers. For acronym, it's the acronym which is getting hallucinated. Then in the generated column, like I said, so if I give this prompt, earthquake in Turkey, it says there is this rescuer, Hassan, and he said something, but then there is no evidence that this person, Hassan, exists. Then we have virtual voice, where the prompt, say for instance, is Pfizer press release on COVID-19 vaccine, and the AI generated text says Pfizer CEO said something. But the reality is Pfizer CEO never said this. So this is the case where it's quoting someone where it he or she never said anything like that. Then we have geographic erratum, where, say, for instance, here, Prime Minister of the UK visiting India, and then he or she, or whoever the prime minister is say scheduled to meet, pay a visit to Pentagon in India, but then Pentagon is in the headquarters of in Washington D.C., not in India. So if the location is getting hallucinated, we call it geographic erratum. And then the final one is time wrap. So this, I think this example is taken from 2023 or late 2022. So USA on Ukraine war, the AI generated text says President Barack Obama says that US will not put troops in Ukraine. But during this wartime, the actual president, US president, was Joe Biden and not Barack Obama. So if there is some kind of conflict between the time line or time period during which something happened, we call it the time wrap issue.
Quick question or comment. In the example on the top left, do you mean 2,000 people, roughly 10%? Do you really mean 200 people? In your fact, is the fact, I mean, does Twitter really have only 2,000 employees worldwide? That seems too low.
So, I mean, so this could be something to do with a particular team or particular department or particular, say, branch in some specific location. Yeah, not worldwide.
Okay, thank you.
So based on this overall taxonomy, where we had three verticals, and orientation, categories, and degrees, we propose a huge HILT data set. It's called hallucination elicitation data set. And for constructing this data set, we chose 15 contemporary large language models. Again, just I'll repeat that this work was done early last year in 2023. And these were the latest language models back then, not anymore. Like few of them are deprecated, few of them, like Llama today has Llama 3.1. But these are some state of the art LLMs back then. And we chose these 15 language models to construct our data set. And these are the statistics. So basically what we did is, for factually correct, so if we look at the taxonomy, we had two main orientations. Initially, we have factually correct, which is factual mirage, and then we have silver lining where the prompt itself is incorrect. So for factually correct prompts, we chose New York Times tweets. And the reason for choosing New York Times is basically it's a news data set and it's pretty popular and it was easily available. And it's a large data set where we had a good time period where from which we chose these tweets. And for silver lining case, where the prompts themselves are incorrect, we took PolitiFact dataset, where we from where we construct the cases for silver lining. So based on these 15 language models and these two data sets, we chose 2,500 each for New York Times Tweet and PolitiFact. So a total of 5,000 prompts. And then for 15 language models, we constructed a data set of 75,000 text passages. And for each of the subcategories, as in intrinsic, extrinsic, for factual mirage, intrinsic, extrinsic, for silver lining. And then for the 6 categories, we have these numbers. And just a quick point to note here is these annotations were done at the sentence level. So if there is any, so we also put this in our limitations where if a sentence has, say, two kinds of hallucinations, a single sentence, we discard such cases and we only retain those sentences where it only has a single kind of hallucination. So these are the annotation guidelines where we have orientation. So in the very first colorful figure where we saw there is orientation, category, and degree. So these are the annotation guidelines. So basically we have if there is no hallucination, it's 0. If it's intrinsic, it's 1. If it's extrinsic, it's 2. For categorical annotations, if there is no hallucination, it's 0. And then based on the vertical we saw, we just number the categories. For degree, we just go with 0 for mild, 1 for moderate, and 2 for alarming. And we had 3 graduate students. So we have these inter-annotator agreements for New York Times tweet and PolitiFact dataset. And we also used Amazon Mechanical Turk. So having said this about the dataset construction, I'll just quickly move forward to the quantification part. So far we saw the characterization where we construct this large benchmark. Now we want to quantify the LLM's tendency, which is to hallucinate. So we say that this is the vulnerability of the LLM, and how do we measure this vulnerability? Again, I'll just quickly repeat that this paper is from the last year, so there wasn't any such metric. Today there are a few, but then we are the first ones to propose this HVI. It's called Hallucination Vulnerability Index, and it basically measures the vulnerability of a given LLM to hallucinate. So these are some results we have, and I'll just discuss shortly how we arrive at these numbers. But what we see from these plots here is we have two categories or two different types of prompts, factually correct and factually incorrect. And then on the right, you will see 6 categories, and then how each category has is vulnerable differently for different. So these numbers just indicate the HVI, and these are some results we obtained from our HVI formulation. So we see on the x-axis, we have 15 language models, which I have already discussed earlier. And then on the y-axis, we have HVI ranging between 0 and 100. On the very right, you will see all the 6 categories. So basically, the main message from this plot is how each language model hallucinates differently for each of the 6 categories for 2 different scenarios where the prompt is either factually correct or incorrect. And these are some implications. So I won't go into the details, but we see that larger language models, so I'll just quickly just summarize here, are prone to both orientations of hallucinations. Then the last point here to look into specifically is for smaller LLMs like say T5, Dolly, uh, the categories such as generated golem, virtual voice, geographic, erratum are rarely hallucinating. So these are just some quick takeaways from the HVI of the language models.
So, Vipula, I would like to, I wonder whether we can observe any connection with the corpus that they might have used, which they don't publish, of course, so it's very hard. And the parameter space or size of the model, and if we can make any observation, even though it will be not it will be very difficult to make those observations very concrete because the models may not have published those information, but something to think about and see if we can make any conjecture.
Yes, Dr. Shet. So we actually have this not ablation, but kind of a study where we assess. So I'll just quickly to answer your question quickly. So this is the study we did in parallel, where we just wanted to see because this was pretty interesting. Everyone was asking, how does the size matter for LLMs hallucination vulnerability? And according to our results, we see that there is no fixed trend. Like we cannot draw a direct correlation between the size and HVI. So we cannot say that larger a model, more it hallucinates, or vice versa. Right? We also cannot say that larger a model, less it hallucinates. So what we observed from this study is if the model is using something like RLHF, like human feedback mechanism, there is a possibility that even if the model is large, it hallucinates less. So our finding from this particular setup was if we involve some kind of human feedback, even if the model is big, it hallucinates less. But then answering the other part of your question, where you mentioned if there is any way we can have some kind of correlation between the data source used and hallucination, that is something we can definitely pursue in the future. But as scope of this work, the only data set we have used is, like I said, New York Times tweets and PolitiFact. There is something in the chat. Okay, Deepa, I'll come to your
Just a
question.
quick suggestion, Vipula. Maybe you speed up a bit because you have a lot of content and it's already half an hour.
So yeah. Okay, how do I go to previous slide? Okay. Okay. So I'll just quickly wrap up the quantification section. So these are the results we obtained for the HVI ranking. And we see here that there is no direct relation between size and HVI. And then we just rank these LLMs ranging from low to high. I want to spend some time here on the equation. So this is the equation for calculating HVI. And if we look at n of x is a total number of hallucinations. And then the only cases which are of particular interest to us is the extrinsic part because those are highly vulnerable. So we just take both extrinsic for factual mirage and extrinsic for silver lining. And basically what we are doing here is, I'll just point out. So we take the total number of hallucinations and then we subtract the extrinsic factual mirage cases from the total number. And we do likewise for even the silver lining. And then we calculate the probability of, say, extrinsic factual mirage. So so to calculate this probability, this is number of these cases by divided by the total number of hallucinations. And we do the same thing for silver lining as well. And then these delta 1 and delta 2, we call them as damping factors. And why do we have them? So the idea here is we want to rank the language models. And then this is not an absolute kind of ranking, it's a relative ranking. So basically, we want to say that how does, say, for instance, Llama perform as compared to, say, T5, right? We don't want to just say, okay, T5 is so and so is Llama, but we want to find out how they compare with respect to each other. So we have these damping factors, and then we initially, so I have some more details in the paper, but just to quickly summarize, we set their initial values to 0, and we quickly calculate the mean and standard deviation for all the 15 language model. And then we just use those and then re-rank all the 15 language models. So what we saw here was the result of that re-ranking strategy. So this is
Excuse
how we
me.
are running.
Um, could you please go back 2 slides?
This one?
No, one more. Still one more. Yeah, there's yeah. I still don't understand this chart. No, I don't understand why there is a single number on top in blue, what the different lines stand for, what the y-axis indicates.
Okay, so I think I can repeat.
Thank you.
So, sure. So these are the HVI numbers, and the range is the range is between 0 and 100. So each number you see at the top is basically that HVI. So y-axis is HVI, x-axis is all the 50 language models.
Yes.
And the reason you see only single number for each model is because we only select the max. So you won't see any value, say for here, yellow or red, right? We only select the ones which are leading. And then what are these colored lines? These colored lines are, so if you look at right, so these are the categories which we discussed in the initial taxonomy. So the message here is, how does HVI perform for all 15 language models for different categories for two separate cases of factually correct and factually incorrect prompts?
So one thing that confuses me then, based on the formula, and is um, HVI seems to take into account different kinds of hallucinations, but here you have curves or numbers really for each different kind of hallucination. You have an HVI for each kind of hallucination, or is that indicating something other than an HVI, like just a percentage of cases in which you have hallucinations?
No, you are absolutely correct. So even though the formula only shows EFM and ESL, the finer granularity is for each of the 6 categories. And so you see
Okay.
these 6 lines.
Okay. Thank you.
Okay. Yes, I think I discussed this part. So yeah, so now I'll quickly move on to, because we are literally low on time. So I just want to discuss the idea behind the black box and gray box techniques we've used to address the problem of hallucination. But before that, I just want to quickly uh, give the background or higher level understanding of what exactly we are doing and why we are doing. So in the context of NLP, we have these entropy points or entropy words where the probability with which they are predicted varies. So this is one quick example, and why we are doing this, because this is necessary to understand further slides. So high versus low entropy points. In the first example, sentence one, we see Paris is the mask of France, and in the second sentence, I saw a mask last night. So the probability with which capital is predicted versus the probabilities with which ghost, vision, light, woman, vampire are predicted are pretty different. So if we see in the first sentence, capital is predicted with the highest probability. So basically, this is an example of low entropy word, which means it's highly certain. On the other hand, high entropy words, which is the second sentence, it means the uncertainty is high and certainty is low. So, from our experiments, what we have observed is if there are high entropy points, which translates to high uncertainty, it basically boils down to the problem of, or to the challenge of LLMs hallucinating. And the our understanding behind this is there is something called as concrete words. So in the context of linguistics, if we look at abstract versus concrete words, words like say tangible, apple, dog, something we can touch or see, these are highly concrete words, and the numbers beside them in blue boxes, those are concreteness scores. On the other hand, abstract words, which are kind of intangible. So, justice, love, happiness, courage, wisdom. These are abstract words. So, these abstract words tend to be quite uncertain. On the other hand, concrete words are quite certain. So, translating this logic to high versus low entropy points, this I just wanted to quickly walk through because this forms the basis of our black box technique, where basically we try to address hallucination by using these entropy points. What we basically do here and why we do it is, so since we are using, say, black box models or closed models like, say, GPT-3, GPT 3.5, these are not open source. So for such proprietary models, if we want to get inside the model and tweak the entropy points, it's difficult. So given this understanding, what we are trying to do here is go for smaller language models which are openly available, and at the same time their tendency to hallucinate, basically HVI, is low as well. So we do this kind of study where we pick smaller open language models where we first use a language model to detect high entropy points and then replace those high entropy points with low entropy points. And this idea basically helps us mitigate some hallucinations. And these are the numbers where we see, so for the Albert and distilled Roberta, we have the maximum drop in hallucination. So this technique we call black box technique. The reason being we are completely using only the language models and we don't use any kind of external information. On the other hand, if we want to use some kind of uh, extra external information, because sometimes the language models by themselves may not be self-contained, and if we want to use some, say, current news or current something that happened, say, yesterday, and I don't have that information stored inside my model, then I go for, say, gray box technique, and it's called gray box because we are using some, say, web resources and so on. So one quick walkthrough is we take the prompt and we give it to Google search engine. We retrieve some top 20 results, and there are more details to it, but I'll just quickly wrap up or summarize here. So we rank these sentences based on the similarity measure, which is cosine similarity, and then in parallel. So this happens in parallel on the, on, say, left hand side or on one side, we have prompt being fed to the language model, and then the same prompt is being fed to Google search engine, and then we merge these two results. We do entailment here, and then based on whatever majority votes we have, we say either it's hallucinated, or if it's not, or there is not enough information to support our case. So this is another technique where we use some external information. Yeah, and these are some results. So this is just an extension of what we saw earlier, but now in addition to only showing HVI, here we show the black box versus gray box techniques, how effective they are in curbing hallucinations for different categories for both factually correct and factually incorrect prompts. So we see some drops here in both cases and for both methods. So entropy BB is black box and factuality GB is gray box method. And then this is an example. So we have used the same example. So I'm just following with that itself. So this example basically illustrates how effective or how these two methods work for a prompt. Say USS stands on Ukraine-Russia war. And then this is the hallucinated text, which is basically the text generated by a language model. And then we have these two methods. So I just want to, what I want to highlight here is these are the high entropy points. And based on what I discussed earlier, high entropy points tend to hallucinate. So we have here in pink, so this is basically the hallucinated fragments. So that's that. And then we have replaced text from our black box method, where we just look at the high entropy points and replace them with low entropy points. So this is the black box method. And then we have our factuality method where we use external information using textual entailment. So this is a quick walkthrough of the example using both techniques. So this is something we had interesting results because if this basically shows how we can address hallucination using only the language models or language models plus some extra information.
Excuse me, can you please explain how entropy is used? I mean, what is entropy for these phrases?
Right. So
I
I
actually
think
have the same question. I don't understand how this approach works. And I know you explain entropy, but like putting it in the approach, um, yeah, I don't understand either.
sure. So basically, if we go back to this slide, we have high and low entropy points. So I'll just translate this. So high entropy is, say, let's just in simple terms, it's bad, as in it's uncertain. So the chances of hallucination with high entropy points is more. On the other hand, the safer
Do you have empirical results? Like, is this the case that that high entropy points are associated with higher degree of hallucination, or is it a hypothesis?
Oh, no, so we have some numbers here. So basically, here what we are doing is we look at these high entropy points and we take a smaller language model. The first, so we have rows and columns and we work in pairs here. So on the say left hand side, we have say Albert model. We use this and we look at the high entropy points. Then let's say I'm using this Distil-Roberta model. I look at those high entropy points and then I generate text with low entropy points, uh, as in low confidence or more certainty. And then I replace those high entropy points with low entropy points, if that answers your question.
Yeah, no, it doesn't, because so you're saying you're studying hallucination is GPT-3, so you don't have the GPT entropy, you don't have the probabilities. And I understand what you're saying. You're using a smaller model, and you're asking, is the smaller model more uncertain on this word? And so that's a fine approximation, but I think the basic hypothesis is high entropy points lead to more hallucination. And so if you use any of these models, you have a table that shows the model that predicts entropy, and then GPT outputs ranked by the hallucination. So do we have empirical evidence that entropy predicted by another model, which is an approximation, is associated, like, is the what you're fixing, is there evidence that the problem is where you're fixing the problem? Does this make sense as a question as we're trying to understand the
I
approach?
think I partially understand your question. So basically, what you're asking is whether I have any kind of results where I show how entropy is related to hallucination.
Correct. And that's not a random question. It's based on the assumption you're saying, I need to fix the high entropy points. And as a scientist, I'm saying, like, are you sure? Did you measure? Like, have you actually established that these are the points where problems occur?
So I think this could partly answer your question. So what we looked at is the concreteness scores. And then one observation is if the concreteness of a sentence is high, I mean, if we have more concrete words, then it hallucinates less. But then if it has less concrete words, then it hallucinates more. And then my understanding is we can translate the idea of concreteness to perhaps entropy, where it's either highly uncertain versus certain. But to answer your specific question, we don't have direct results for any relation between entropy versus HVI or something to do with hallucination.
And do you have the table of concreteness and abstractness related to hallucination? Because really, the slide just introduces this concept in psychology, concrete and abstract, but it doesn't link it to the phenomenon that you're using, studying.
No, I do not have a slide right now for concreteness.
Marco, I'm ready to move on. Is it okay, or do you want?
Oh, yes, of course. Thank you. Thank you for the question. Yes, please, let's move on.
Okay. Yeah, we can discuss more after the 1 hour mark. So I think we only have 10 minutes, I guess. So I just want to quickly, yeah. So this was the entire description of the initial two parts where we characterized and quantified. Then the third part is how do we avoid hallucination? So basically, this is a novel prompting technique we call sorry, come again. And the rationale behind this is the LLM's ability to comprehend a given prompt in the first place. And then if it does, then how well does it comprehend? And then if it understands the prompt itself, then there is a chance that it won't hallucinate. Versus if it does not understand the prompt itself, it may hallucinate more. So basically, the analogy is from human understanding. For instance, if you ask me something and if I understand it well, I can give you the correct answer. But if I don't understand your question itself in the first place, there is a chance I'll say something which does not align with what you asked, and that can be put as some kind of incorrect or manipulated response. So in this example, what we are looking at here is we have an original prompt and then we have a reformulated prompt. So basically, like I said, we are just trying to understand here whether the language model can understand the prompt itself and how do we assess the LLM's comprehension is we basically look at, so this is the further line of work I have been pursuing. So here we look at 3 linguistic scores called readability, formality, and concreteness. So how well or how readable the prompt is, how much formality it has, and how much concreteness the prompt has. So given these 3 features, we see if we have certain numbers, the linguistic scores, and we have some results based on how hallucination relates with these linguistic features. So in the first prompt, which is the original prompt, we have some numbers where we have 29.46 as the readability, 53.5 is the formality, and concreteness is 3.27, where the range for first two is 0 and 100, and for concreteness, it's between 1 and 5. And we see that the first prompt hallucinates is generating some fancy response. On the other hand, if we reformulate the prompt based on these features, it generates the correct response, which is shown here in green. So basically, if you compare the linguistic scores on the left and right, we'll see that on the right, the readability has increased, concreteness has increased, but the formality decreases. So basically, we are just trying to see if the prompt is more readable, and if the prompt is more concrete, then does it hallucinate less? Does it mean that the language model understands the prompt better in the first place, and hence it hallucinates less? So in this prompting technique, we just call it sorry, come again. It basically means I did not follow you. Can you please repeat, or can you please rephrase your question? And then this is the example, which individuals possess the ships that were part of the Boston Tea Party. And then on the right, we see how the scores change. And we even see something called as pause token. I'll come to it soon. So that's basically the main takeaway of this work, which we call avoidance. So here we have an algorithm built for finding the optimal paraphrased prompt. So given a prompt, we paraphrase it, and then we decide which is the optimal paraphrase we should consider, which will not or less hallucinate. And then we use the integrated gradients, and we compute a comprehension score here. Basically, it means how well the language model understands a given prompt. And then based on this iterations here, we find out the most optimal paraphrased prompt. Again, with the same example, we have here which individuals possessed the ships that were part of the Boston Tea Party, and we generate 5 paraphrases. And then if we look here, we have this integrated gradients. Basically, it's something to do in the context of explainability, where we look at how important each token is. And we have used 3 different variants of integrated gradients. So IG is just the plain vanilla, the first paper which came out on integrated gradients. Then we have discretized, and then we have sequential integrated gradients. So what we do here is take an average of these 3 just to make sure that we incorporate each of them, because not one single method is perfect. And then we have the word distribution here based on the word importance scores, and then we choose the most optimal paraphrase. So we have one working example which has more details, but this is just a higher overview. In the interest of time, I just want to quickly even explain this, where in the first figure we saw pause tokens. So the rationale behind introducing pause tokens is another line of thought, as in lengthier the prompt, it's difficult just as us humans to understand. So does the LLM. So how about we just break the prompt, right? So there is one initial work, I think from Google research, where they introduce this idea of pause tokens, but we go a step further and we say, okay, How do we use it in the context of, first of all, hallucinations, and second, how do we use it where we have some kind of linguistic features? So here we have certain thought process where we say, okay, where to introduce these pause tokens, not just randomly, then how many pause tokens to introduce, and so on. So if we look at this specific example, since we are using the same example, who were the owners of the ships associated with the Boston Tea Party? And we calculate something called as abstractness score. So we have that formula. And then it's basically a combination of formality and concreteness and the length of the words. So you'll see here for this particular part, we have some 50.5 as the formality score. Concreteness score is 2.92, and the length of the words before this pause token is just 4. And then we look at the preposition conjunct, and then this is where we break the longer prompt and we introduce the pause tokens. Now, how many pause tokens to introduce? That is something we also described as to whether if it's low abstractness scores, whether it's high, whether it's mid-range, and then based on that, those kind of results, we decide how many to introduce. And then similarly, we have some scores here, and we have 3 words, and then we introduce some pause tokens here, and finally, so basically we broke this longer prompt into 3 chunks. Think so. Just a quick question: how are we doing on time? Because I have more.
So you've gone for about 50 minutes. So I would like for you to try to conclude in about 10 to keep it to an hour.
Okay,
10 minutes.
sure. Sounds good. Thank you. So to use these pause tokens, we introduce something called as reverse knowledge distillation. It's just a name, but what we are basically doing here is we are fine-tuning the usage of pause tokens in our LLMs. So if you look on the left, we have, so the idea why we are doing this, first of all, like before I go into the method, the idea is simple. We just want to use pause tokens, but then there are different methods, say LoRa, QLoRa, and so on, because fine-tuning these language models is, first of all, extremely computationally expensive, and we don't want to get into fine-tuning all the layers. So we just want to fine-tune the last layer here, and that's basically the rationale. And we use a smaller language model, and which acts as the teacher model. So there is something called as knowledge distillation, which means you take a teacher model and you explain or you teach the student model, and that's how it works. But in a typical setup, the teacher model is a larger language model with more parameters, and the student model is a smaller language model with fewer parameters. But in our case, the setup is reversed. We use a smaller language model to teach the larger language models. And why so? Because in our experiments, we are using the 15 or whatever number we have, I think, we have large language models. So we use a teacher small language model to teach a large student language model. And we freeze all the layers except for the last layer. And then we have 2 loss functions here. One is the distillation loss. Basically, it's the kind of, you can call it as a transfer between student and teacher. And then we have the student loss, which is between the output layer and the final target it learns from. So this is only to fine-tune the large language model for using pause tokens. And that's about it. And we experimented with LoRa, QA LoRa, and then we have our reverse knowledge distillation method. And the experiments done are for, so we have this setup where basically the final task is textual entailment. So I can actually quickly walk you through this and then go back to the result slide. So when we say avoidance, basically what we are trying to do is completely avoid hallucination. And the entire process boils down to we take the original prompt and then we paraphrase it. So there are two parts to it. The first A part here in red, we see how do we find out the optimal paraphrased prompt. And then given this paraphrased prompt, the optimal prompt, then we evaluate it for hallucination. So you take this prompt, you paraphrase it, you generate 5 paraphrases, then we run our optimal paraphrase algorithm, where based on the integrated gradients, we select the most optimal prompt. Now we take this optimal prompt, and then this is something similar to what we saw in the gray box technique, where we feed this prompt to Google search engine. We retrieve top 20 search results, then we rank them, and we do some kind of cosine similarity. At the same time, we also feed this prompt to the PAUSE fine-tuned language model, which was basically the previous slide, reverse knowledge distillation. And then we generate we have some AI generated text. So based on this and based on what we get from Google search result, we just do a textual entailment. And then based on the final scores, it's either hallucinating, not hallucinating, or there is not enough information to support the case. So that's neutral. So the final task is textual entailment, and these are the results for neutral, refute, and support, and for 4 different categories. So if we look at what happens when we introduce pause tokens, what happens with just the original prompt, what happens with the optimal prompt, and then what happens with these techniques when we have pause tokens. So the purple or this blue color indicates support, and these numbers are basically, they are high, the performance is more as compared to without pause tokens. So that's the main message here. And then the final section is on hallucination detection. So I can actually quickly explain a few slides here. So the main idea for factual entailment, or a factoid as we call it. So if we quickly look at this example, same example, I have used the same example throughout the entire presentation. Say the prompt is USA stands on Ukraine-Russia war, and then we have some AI-generated text, and we have some web retrieved document. Now, the challenge here is if we use any kind of classical textual entailment model, if I do textual entailment on these 2 sentences, it's giving me neutral, which in reality, it should give me refute. So the current detection methods, they mainly have this idea of breaking a prompt into so-called atomic facts. I don't think I have it right now, but we can discuss more in our discussion time. But so what it does is, so let's say it has this sentence, it's going to break it into Barack Obama, US, Ukraine, right? And then for this sentence, it's just going to break into some facts, which are, say, Joe Biden, US, Russian troops, Ukraine, and so on. So with this kind of detection approach, what happens is, if I have individual facts, then there is no relationship between them. So first of all, we lose that. So now if I want to do some kind of hallucination detection, when I have this entire sentence, I know that Barack Obama declared, or say Joe Biden said. But if I break this sentence into parts, I'll have a difficult time, or rather, I have a difficult time in determining who said what. So either it could be Barack Obama, or it could be, say, even Bill Clinton, right? So this is the major limitation of the current detection methods, where they simply break a prompt into atomic facts. In our method, we show that limitation and we say that, okay, how do we overcome it? And we propose something called as factual entailment, where it has three subparts to it. We do span detection, that's the main highlight. Then we even classify the kind of hallucination it has. And then we have a textual entailment model. So the main idea here is we try to look at the spans in the text which are not in agreement, kind of. So for this task, I'll even explain in the further slides, but we train the model in a way that it gives this span where there is difference, and then it also gives the actual scores. So here it predicted neutral for these two sentences, but in reality it should have been refuted. But so if we do factual entailment, it overcomes the limitation of the classical model and it gives refute as the output. And not only that, but it also gives us the span and it gives us the category of hallucination. So here it's giving us the temporal issue, which we saw in few of the very early slides, right? So Joe Biden and Barack Obama, they are from different timelines, and that is what it's predicting here as temporal issue. So these are just some examples where we take the prompt and we generate a synthetic data set. So basically the data set is positive negative pairs where it can, the model can basically learn. And these are some statistics from Hill data set. We extended and we synthesize the data set. We generate a synthetic data set. And this is the multitask framework for factual entailment, where we take these two prompts, where one is, say, the first prompt, and the second one, the one here is the AI generated text, and this is the web retrieved document. We use longer embeddings, and then we have SpanBERT. Then we do some kind of, we have loss functions here. Yeah, we do joint training, and then we get the output for 3 different tasks. And these are the baseline improvements. So we only consider the SOTA, as in the classical textual entailment models, and then we have factual entailment and hallucination classification for all the 4 categories, and the final one is for average. And then we also propose an automatic HVI in a similar fashion to what we saw for only HVI. So we have these categories, and then we have HVI on the y-axis between 0 and 100, and then we have 15 language models. And following the same line of thought, we have re-ranked based on auto HVI, and then we have a different equation where all we see, the only difference is, instead of those extrinsic factual mirage and extrinsic silver lining, we have these 4 specific categories of hallucination. I think we are almost there. So having discussed what I have done so far, these are some more works I am currently actively pursuing. One is 2 are in the line of mitigation, where we are using text diffusion models to mitigate hallucination. The second line of research is into policy optimization, where we use some optimization technique which can help mitigate hallucination. And the third one, as I discussed, is extending this language-specific work to multimodal, and we'll be looking into images and video hallucination as well. So So these are some publications related to my dissertation, and we see, so green are the published ones. So far there is just one paper which is published in EMNLP last year, and there are two which are under review. Then we also delivered a tutorial at El Cooling in May on hallucinations. And then these are the preprints. This survey paper got some good impact, and we are also planning to submit it soon. The timeline for my dissertation is have the first draft ready by February 25, propose final defense sometime in March 25, and then submit the dissertation to the grad school sometime in April 25, and hopefully graduate by May. So I think that's pretty much it, and thank you for your time and attention, and I'm open to questions.
Thank you. So yeah, you took, I believe, approximately 1 hour and 4 minutes. That was a long presentation. Questions. I would suggest that we open the floor to the whole audience. Then we'll have a time for the committee to be alone with you, Ms. Raute. So maybe we should encourage members of the audience